So now we're going to talk a little bit more going forward into the closed-loop systems and identify sensory contributions. And sensory contributions, right, are touch, sight, hearing. And a lot of times what we figure and look at in here are auditory and visual. So these sensory receptors for movement come in a couple different forms. And you have your interoceptors, which is the state of your internal organs, exteroceptors, which is the movement of objects in the environment. And then one of the things we rely on a lot is proprioceptors, and these are things that are focused on our own movements. And through this process, the proprioceptors give us feedback on where our movements or how our body parts are doing in time. And two of the major ones for that are GTOs and muscle splitters for our proprioceptors. But if we look at vision, this is a very effective way to receive exteroceptor feedback, so feedback about our environment. And we have two different types of roots or systems, and that's dorsal and ventral. So it's very important that you understand the difference between these two in a basic standpoint. And so the dorsal is that peripheral vision, right? So it's that visual field at 180 degrees. It's not one that requires focus. It's just you can see things in your outside, and then there's also low light. So this one does not require light, and that's simply because of the focus concept, right? And the difference with the ventral is that it's limited to your central vision, and this is really where you find the contrast, the focus, and it needs sufficient light to really identify what you're looking on or focusing on. And then this is what you use. So the ventral system is what you're using for object identification based on that contrast and focus. And it really has an idea with your conscious perception of the environment. It is what you are directly looking at, where the dorsal and that peripheral happen to be within that 180 degrees. So if I'm looking at a window, I can see the walls or see everything around me, the grass, the green. So just understand the difference, and dorsal is going to be your peripheral or your 180 degrees, and then central is what you're actually looking on, it's what you're focusing on. Therefore, it requires a lot of light. Now, the idea is both project some sort of environmental feedback by means of the retina, and these go back to the primary visual cortex of the brain. Now, these type of comments here, it's not really, these are for more of an anatomy, physiology component of what we're doing, but I really want you to just focus on mainly that the dorsal and ventral roots are focused on either the central vision or the peripheral vision, which one requires light, which one doesn't require light, which one is more for focus. So just a little breakdown, and this is very rudimentary, and for a greater understanding of this, you go back to your physiology days. But so you have your dorsal stream hits the posterior parietal cortex, and then the ventral stream, your inferotemporal cortex, and that's really where as they go through the retina and bounce back to the brain, and the brain stem back in the back of the brain, they hit these individual streams and help you identify what your environmental is from the vision. So again, ventral, which is involved in the object identification, is your perception, and then the dorsal is a control of movement, and that is more focused on your action. So understanding those components in ventral perception, and then dorsal more about your action and control of movement. So one of the things that we look at is that effect on vision. And one of the big things is that visual illusions and the biases of the perceptual judgment. And I'm sure that a number of you have seen a number of these that we're going real quick before, and so you probably know the answer, right? But if you didn't, and you look at these two, and what we're going to talk about is the internal line here. And if you look at these quickly and we go through, if I label this A and this one B, it looks like A, the center line is a little bit longer, but in actuality, both lines are the same length. It just happens to be the perception based on these other lines. Same concept here, right? So if we look at it, and we look at these central two, it looks like there might be a difference in length based on how they are perceived closer to the apex because of the other lines. And then the same with these two. Because at this point here, you have a split, our eyes may make us think that the vertical line is longer than the horizontal line, but in fact they are the same. And this is a task down here in the bottom with these circles, and we'll see this come up in the third module when we start talking about some of the golf tasks that we do. But the key is these center circles, and the idea is that this on the left-hand side, which I just labeled A, seems to be larger circle because the ones around it are so small, where the one on the right, labeled B, this one in the center here, seems to be a smaller because of the perception of those on the outside. So our perception is that these two circles are not the same size, but in fact they are, right? And so we'll talk about this illusion going forward when we talk about the golf stuff in later modules. So then one of the things that we're going to talk about is the effect of the vision and tracking coming back from a ball. And what we're going to, and this is from a baseball perspective, right? And so and that's where a lot of this research comes from, but understanding that this could be with any ball that we look at. But think about this. So here's a ball, right? And the way that we see this ball is there are light rays that travel on top of the ball and light rays that travel on the bottom of the ball. And then what we're going to look at is if we have the center of the eye that goes directly towards the center of the ball, there are two alphas, and these alphas are angles, alpha 1 and alpha 2. And so what we see is this, the angle of perception of the top and bottom ball are going to tell us a lot. And basically it's the idea of that this information drawn from the visual tracking gives us information about the temporal component of when the ball will arrive in our location. And we're going to revert to this as time to contact, and this is a T sub C for time to contact. And so what happens is the angles, and this should be angle, not angel, of the light rays around the object are going to tell us if the ball is coming forward towards us, whether it's staying stationary or whether it's retreating, and also whether it's going up or down. But so this direction of travel is going to tell us a couple of things, and the idea is looming, stationary, receding. So looming is what you see here is a direction of motion. And so imagine this, if this ball is looming or coming towards us, these angles, alpha 1 and alpha 2, will increase. So the angle will increase when it's looming, both of them, if it's coming straight at us. Stationary object, there will be no change, so it will be equal. They will stay the same angle. Whereas if it was receding, those angles would decrease because this ball would be going this direction, these angles would be decreasing. So make sure you understand how we're going to utilize these angles here to give us an information about the temporal component of time to contact by understanding whether or not the angles are increasing or decreasing. And that tells us whether or not the ball is coming closer or further away from us. Now, I'm not going to ask you to remember this tau, what tau is, or remember this graph. And if I ever give you a graph and I want you to memorize it or really understand, I'll make sure I let you know. But this idea of time to contact is proportional to the reciprocal of the proportionate rate of expansion of the retinal image. And that's what you have here, right? So these angles, you have a constant. But just understand that as the velocity increases, the tau also increases at the time to contact in seconds. So just understand that this is, if you go into the article, you can read more about this tau coupling and how to calculate it. But we're going to really only understand what I want you to focus on is the angle at which we're using our vision in the ball to identify when the time to contact happens. So this tau coupling, it's a goal-directed movement, and it's really the closing of two gaps. And we'll talk about these two gaps that we have to. But think about this. Think about an outfielder catching the ball. And so the two gaps are what? Well, the two gaps are if I'm an outfielder, and so this is where the outfielder is. This is where home plate is. So initially, the ball is hit. Okay, and the fielder has to run this direction. Okay, so the gap is the fielder predicts where they think that the ball is going to land. So the two gaps are the time to contact the ball takes to that location and the time to contact for the runner to get there. So there's the time to contact, or the two gaps are the person running and the ball running. And that would be the location it takes to get to the ball. So how does this visual feedback aid in movement? And so you have the initial impulse phase and driven toward target impulsively. Then you have the current control phase, and that feedback provides spatial information to the current path. And so some of the studies, and this one was Woodworth in 1899, but the idea is, so on the x-axis you have time to target, and then you have the average error in millimeters, right? And so when the eyes are closed versus the eyes are open, the error with the eyes open decreases drastically over the eyes closed when the targets, especially the longer it is for the time of the target. And so as early on, when there's a short difference in time or short duration of when the location is towards the target, there's not much of an error in millimeters. But as time increases through the process, there is a much greater error, or influence, I would say, towards the eyes open, right? And that's what I meant to say. And so what happens is these critical points are areas and where you see the division, the rapid division between the two. And so for this one, it's probably around 500 milliseconds. And then we have over here the same kind of display where the lights are on and the lights are off. So therefore, remember we talked about the ability of light to really allow you to focus in. You create, as we increase in time, the ability to hit the target, because you're able to see, are affected, and you have a better probability, a reduced probability of missing the target over time with the lights on. But again, what these bold are going to tell you is when the milliseconds are the actual time that you're taking to do this. It's not affected early on with sight, but as time goes on, sight has become a major, or vision is becoming a major effect. And this is because you have time to process that visual feedback. And now, this ability to process that feedback is dependent on a couple of things: the nature of the task, the type of visual information, remember, whether it is kind of the dorsal or peripheral versus very focused and ventral style, and then the predictability of the information. And so if something is very cyclical and predictable, it's much better and easier for us to process that visual feedback versus things that are random or kind of the open chain kind of world or open environment. Now these all affect the speed and effectiveness of these aiming tasks, and so a lot of times you'll see people who are better able to adjust for wind do better in shooting competitions, especially archery or rifle shooting. And then so now the other concept I want to talk about is this idea of vision as an anticipatory kind of action. And so you have, again, the time to contact, which is a temporal. So when do you intercept? And then you have the spatial, and that's where. And so when we talk about the football player, or the baseball player and the baseball outfielder, the where is now, he predicts the ball is going to land in a certain spot. So the where is he going to focus his attention, and what gap, the gap that it's going to change, the outfielder is going to change towards that place is the where. And again, here's just some more depictions of that image. And this is the paper, and I'll make sure I go ahead and post this paper, the McLeod and Deans, that really talk about this idea. And so again, here's gap one, the outfielder towards where the ball is going to land, that where. And then the ball is gap two, and so they both have time components. How long is it going to take, or how fast is this person need to run? And then the ball's trajectory and what time the ball is going to get there. Because the time of the ball, determines where exactly this person needs to run in the outfield, and so this is the time of the person. Now, when we talk about whole body actions, and we talk about the sensory components, right? So you have vestibular, which is the auditory. It's really what's happening in the canal. We'll talk a little bit about that. And then you have the joint receptors. And these are, again, the kind of GTOs and muscle spindles. And then we have the optical flow and what your really vision is going to be. Now, one of the things that I want to draw your attention to is this study from Lee and Ronson in '74, and what they're really trying to do is really identify the optical flow and how that has to do with whole body action, especially balance and maintaining that balance. And so this study is what happened in here is you have a child that's standing in this room. The floor does not move, right? So that takes away joint receptors and vestibular because the head's not moving, the body's not moving. But instead you have this room that moves around you. And so there's an optical flow illusion that happens during this process. And so what this is meant to show you is that the idea of vision has a great effect on our ability to balance through the environment.